Welcome to the Deep Sleep Discoveries channel. Tonight, let yourself drift into the gentle current of energy, the invisible force that flows through every atom, every star, every breath you take. Energy is the quiet heartbeat of existence itself, neither created nor destroyed, but endlessly transforming, moving through the cosmos in an eternal dance. As you settle into this moment, allow these facts to wash over you like waves on a distant shore, each one a small window into the magnificent tapestry of our universe, where everything is connected by this fundamental force that has existed since time began. Energy cannot be created or destroyed, only transformed from one form to another, a principle so fundamental that it shapes everything in our universe. This law, known as the conservation of energy, means that every bit of energy present at the dawn of time still exists today, flowing and changing through countless forms. The warmth you feel on your skin from sunlight began as nuclear fusion in the sun's core, traveled millions of miles through space, and now gently touches you. Energy is never lost, merely passed along, cycling endlessly through stars and planets, through living things and empty space, in a cosmic dance that has continued for nearly 14 billion years. The word energy comes from the Greek energeia, meaning activity or operation, a term first used by the ancient philosopher Aristotle to describe the capacity for action. For centuries, humans sensed energy's presence without fully understanding it, observing the power in rushing water, the heat of fire, the force of wind against sail. It wasn't until the 1800s that scientists began piecing together the unified concept of energy we know today, recognizing that heat, motion, light, and electricity were all manifestations of the same fundamental phenomenon. The word itself carries within it the essence of what energy is, the ability to make things happen, to cause change, to breathe movement into the stillness of matter. Kinetic energy is the energy of motion, present in everything that moves, from the smallest vibrating atom to the largest spinning galaxy. When you toss a ball through the air, you give it kinetic energy that depends on both its mass and velocity, with faster objects carrying exponentially more energy. A hummingbird's wings beating 50 times per second possess kinetic energy, as does a river flowing steadily toward the sea, as does your own blood coursing quietly through your veins. This energy of movement is everywhere around you, in the breeze stirring curtains, in cars traveling distant highways, in the earth itself as it spins through space at over 1,000 miles per hour. Potential energy is stored energy waiting to be released, like a held breath or a coiled spring containing the promise of future motion. A book resting on a high shelf holds gravitational potential energy, ready to fall if disturbed, while the chemical bonds in the food you ate for dinner store energy that your cells will gradually release. Water behind a dam possesses tremendous potential energy, quiet and patient until the gates open and it rushes forth with force. Even as you rest now, your muscles contain stored chemical energy, your body positioned against gravity's pull, holding potential that could transform into motion at any moment, though for now, it simply waits, peaceful and still. Heat is the transfer of thermal energy between objects of different temperatures, always flowing naturally from warmer to cooler, seeking balance and equilibrium. When you hold a warm cup of tea, thermal energy moves from the liquid into your hands, the molecules in the tea vibrating less as those in your skin vibrate more. This transfer happens constantly around you, the sun warming the earth, your body warming the air, a stove heating a pot of water. Temperature itself is really just a measure of how vigorously molecules are moving and vibrating, their kinetic energy at the microscopic scale creating the sensation of warmth or coldness we experience, a constant exchange of energy seeking harmony. Light is electromagnetic energy that travels in waves and particles simultaneously, a dual nature that puzzled scientists for centuries until quantum mechanics revealed this strange truth. Photons stream from the sun at the speed of light, carrying energy across the void of space without needing any medium to travel through, pure energy in motion. These particles have no mass yet carry momentum, can exert pressure, can be absorbed by your skin and converted into warmth. Light encompasses not just what your eyes can see, but also infrared warmth, ultraviolet rays, radio waves, X-rays and gamma rays, all the same phenomenon at different energies, all rippling through space as electromagnetic radiation. Unwinds Sound is energy that travels through matter in vibrating waves, unable to cross the vacuum of space but moving beautifully through air, water, and solid materials. When you hear a voice or a song, you're sensing compressions and rarefactions in the air, molecules pushed together and pulled apart in rhythmic patterns that carry energy to your eardrums. Sound moves faster through water than air, faster still through steel, the particles in denser materials more efficiently passing vibrations along. Every sound you've ever heard is energy in motion, from the lowest rumble of distant thunder to the highest note a violin can sing, all of it molecules dancing to transfer kinetic energy from source to listener. Chemical energy is stored in the bonds between atoms in molecules, invisible architecture holding matter together and containing tremendous amounts of stored power. The food you eat, the gasoline that powers cars, the wood that burns in fireplaces, all hold chemical energy in their molecular structures, energy that was often captured from sunlight by plants long ago. When these bonds break and reform during chemical reactions, energy releases, sometimes gently as warmth, sometimes explosively as flame. Your own body is a master at harvesting this energy, breaking down molecules with remarkable precision to extract exactly what it needs, releasing energy smoothly and steadily to keep you warm, to keep your heart beating, to power your thoughts. Nuclear energy comes from the bonds that hold atomic nuclei together, forces so powerful that releasing even a tiny fraction can produce enormous energy. Inside an atom's nucleus, protons and neutrons are bound by the strong nuclear force, one of nature's fundamental forces, stronger than gravity or electromagnetism. When these bonds are broken through fission or joined through fusion, the small difference in mass converts to energy according to Einstein's famous equation. This is the power that makes stars shine, that can light entire cities from fuel smaller than your fingertip, energy bound at the very heart of matter itself, in that impossibly tiny space at an atom's core. Electrical energy is the movement of electrons through a conductor, a flow of charged particles that powers much of modern civilization. When you flip a switch, you complete a circuit that allows electrons to rush through wires, their movement creating the energy that lights bulbs, runs computers, charges your devices. Lightning is electrical energy on nature's grand scale, millions of volts bridging sky and earth in spectacular discharge. Inside your own body, nerves transmit signals through controlled flows of electrical charge, thoughts themselves arising from electrical patterns in your brain. This energy that flows through copper wires also flows through you, part of the same electromagnetic force that shapes our universe. Elastic energy is stored in objects that can be stretched or compressed, waiting to spring back to their original shape with force. A drawn bow holds elastic potential energy, the bent wood and stretched string storing the archer's effort until release sends the arrow flying. Rubber bands, springs, trampolines, even your own tendons all store and release elastic energy with each stretch and recoil. This ability to absorb force, hold it briefly then give it back, is how shock absorbers work, how bouncing balls return to your hand, how your body cushions each step you take. The materials remember their shape and fight to return to it, this resistance creating a temporary home for energy. Gravitational energy depends on an object's height and mass, increasing as either grows larger, a form of potential energy that gravity's patient pull creates. A boulder perched on a mountain holds more gravitational potential energy than a pebble on the ground, the height and mass combining to determine how much energy it would release if it fell. Earth's gravity field stores energy in everything it holds up. Clouds suspended in the sky, water pooled in mountain lakes, your own body standing upright. The higher an object sits within a gravitational field, the more energy is stored in its position, waiting for the inevitable pull downward, though for now it simply rests above, holding its elevated state. Mechanical energy is the sum of kinetic and potential energy in a system, the total energy available for doing mechanical work and causing motion. A swinging pendulum constantly converts between these forms, potential energy at the peak of each swing transforming to kinetic energy at the bottom, then back again in endless rhythm. A rolling ball on a hill possesses both energies simultaneously, kinetic from its motion and potential from its height. The total mechanical energy in an ideal system stays constant, energy flowing between forms but never disappearing, though in reality, friction gradually converts it to heat, the pendulum slowing, the ball eventually stopping, mechanical energy giving way to thermal. Radiant energy travels in electromagnetic waves without needing a medium, pure energy propagating through the emptiness of space as oscillating electric and magnetic fields. The sun's radiant energy reaches Earth across 93 million miles of vacuum, photons streaming outward in all directions, spreading light and warmth throughout the solar system. This energy exists across a vast spectrum, from radio waves stretching yards long to gamma rays smaller than atoms, all traveling at light's constant speed. Your body radiates infrared energy constantly, glowing in wavelengths invisible to your eyes but detectable by thermal cameras, each living thing a source of radiant energy, contributing to the universe's endless electromagnetic symphony. Energy density measures how much energy is stored in a given space or mass, a crucial property that determines what makes practical fuel and what doesn't. Uranium has extraordinary energy density, a single kilogram containing millions of times more usable energy than the same mass of coal or wood. Gasoline's relatively high energy density makes it useful for transportation despite its other drawbacks, while batteries struggle with lower energy density, storing far less power in the same space. Fat in your body serves as high-density energy storage, packing more than twice the calories per gram as carbohydrates or proteins, your biology's way of efficiently storing reserves for times of need. The total energy of the universe has remained constant since the Big Bang, neither increasing nor decreasing despite all the transformations occurring every moment. When the cosmos burst into existence nearly 14 billion years ago, it contained a certain amount of energy, and that same total persists today, merely redistributed among countless forms. Stars burn, planets form, life emerges and fades, galaxies collide, yet the grand sum remains unchanged. This conservation speaks to something profound about the nature of reality, that energy is fundamental, eternal, neither created in that first moment nor made since, but somehow present from the very beginning, as essential and permanent as existence itself. Stars generate energy through nuclear fusion, converting hydrogen into helium deep within their blazing cores where temperatures reach millions of degrees. In these furnaces of creation, hydrogen nuclei are squeezed together with such tremendous force that they overcome their natural repulsion and fuse, releasing energy as photons that begin a journey toward the surface. This energy, born in the crushing pressure at a star's heart, may take thousands of years to work its way outward through the dense stellar material, bouncing countless times before finally escaping as light. Every ray of sunshine you've felt began this way, nuclear energy transformed through an epic journey into the gentle warmth on your skin. The sun releases more energy in 1 second than humanity has used in all of history, an output so staggering it challenges comprehension. Our star radiates about 380 septillion joules every second, enough to power human civilization for hundreds of thousands of years, yet this represents merely a tiny fraction of the energy reaching different parts of space. The vast majority of this energy streams past Earth into the cosmic void, warming nothing, lighting nothing, simply spreading outward into the dark. Yet even the small fraction Earth intercepts is more than enough to drive our weather, grow our food, power the cycles of life. The sun is profoundly, almost impossibly generous with its energy, burning steadily for billions of years. Dark energy makes up approximately 68% of all energy in the universe, a mysterious force that seems to be accelerating the expansion of space itself. Scientists discovered this strange energy only recently when they noticed that distant galaxies are not just moving apart, but moving apart faster over time, pushed by something pervading empty space. We call it dark, not because it blocks light, but because we cannot see it, detect it directly, or fully understand what it is, only observe its effects on the cosmos's expansion. This invisible energy, more abundant than all the stars and planets and dark matter combined, shapes the universe's fate, stretching space between galaxies, pulling the cosmos ever outward. A supernova releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime, an explosion so violent it briefly outshines entire galaxies. When a massive star exhausts its fuel, its core collapses in less than a second, then rebounds with such force that the outer layers are hurled into space at tremendous speeds. The energy released in this cosmic catastrophe is almost incomprehensible, more than all the energy from every star in a galaxy combined, concentrated into one fleeting, brilliant moment. These explosions forge heavy elements like gold and iron, scattering them through space where they may eventually form new stars, new planets, perhaps even the building blocks of life. Black holes possess such extreme gravitational pull from their concentrated mass that not even light can escape their event horizon, that boundary beyond which nothing can return. The mass of multiple stars compressed into an impossibly small space creates gravitational fields so intense they warp space-time itself into a deep well from which no escape is possible. Energy that crosses this threshold is lost to the outside universe, trapped beyond reach, adding to the black hole's mass. Yet these cosmic monsters aren't truly black. They glow with hawking radiation at their edges and often have blazing accretion disks of matter spiraling inward, heating to millions of degrees before disappearing forever across that final boundary, energy meeting its strangest fate. Cosmic radiation constantly bathes Earth in high-energy particles from space, remnants of ancient supernovae and other violent cosmic events. These particles, mostly protons and atomic nuclei, travel at nearly the speed of light, carrying tremendous energy across vast distances before striking our atmosphere. When they collide with air molecules, they create cascades of secondary particles that rain down to the surface, passing harmlessly through you as you sleep, invisible messengers from distant corners of the galaxy. Earth's magnetic field and atmosphere shield us from most of this radiation, but it still contributes to the background radiation all living things experience, a gentle cosmic touch connecting us to the universe's most energetic processes. Gravitational waves carry energy rippling through the fabric of space-time itself, created when massive objects like black holes or neutron stars spiral together and merge. These waves stretch and squeeze space as they pass, so subtle that detecting them requires measuring changes smaller than the width of a proton across distances of kilometers. When two black holes collide, they convert several suns' worth of mass directly into gravitational wave energy, sending ripples racing outward at light speed. These waves have been traveling since the universe's earliest moments, passing through planets and stars, through you right now, carrying energy not as particles or electromagnetic radiation, but as oscillations in the very geometry of space and time. Pulsars are cosmic lighthouses spinning rapidly and beaming energy across space, the collapsed cores of massive stars rotating sometimes hundreds of times per second. These neutron stars, each packing more mass than the Sun into a sphere the size of a city, have magnetic fields trillions of times stronger than Earth's, channeling particles and radiation into intense beams from their magnetic poles. As they spin, these beams sweep across space like lighthouse beacons, and if Earth happens to lie in the beam's path, we detect regular pulses of energy, some arriving with such precision they rival atomic clocks. These spinning remnants pour enormous energy into space, gradually slowing over millions of years as their rotational energy radiates away. The cosmic microwave background is ancient energy from the early universe, light that has been traveling through space for over 13 billion years. When the universe was only 380,000 years old, it cooled enough for atoms to form, and light could finally travel freely through space for the first time. That primordial light still fills the universe, though stretched by cosmic expansion into microwaves, creating a faint glow in every direction we look. This ancient energy, nearly uniform in temperature at just 2.7 degrees above absolute zero, is the oldest light we can see. A fossil radiation carrying information about the universe's birth, now arriving at Earth as whispers of energy from the dawn of time. Gamma-ray bursts are the most energetic explosions in the universe, brief flashes that can release as much energy in seconds as the Sun will in its entire existence. These cosmic detonations occur when massive stars collapse or when neutron stars merge, creating jets of energy that beam outward at nearly the speed of light. If a gamma-ray burst occurred in our galaxy and pointed toward Earth, its energy could strip away our ozone layer and cause mass extinction, though fortunately these events are rare and distant. For those few seconds of their peak brilliance, a single gamma-ray burst can outshine all other energy sources in the observable universe combined, nature's most extreme expression of power. Solar wind carries energetic particles streaming from the sun's outer atmosphere, a constant flow of charged particles racing through the solar system at hundreds of miles per second. This wind, composed mostly of electrons and protons, extends the sun's influence far beyond its visible surface, filling the space between planets with dilute plasma. When these particles reach Earth, they interact with our magnetic field, sometimes creating the beautiful auroras that dance across polar skies, green and red curtains of light as solar energy excites atmospheric gases. The solar wind is gentle here, but closer to the sun, this stellar breeze can carry tremendous energy, shaping the environments of inner planets and gradually pushing comet tails to always point away from our star. Nebulae glow with energy as newborn stars ignite within them, vast clouds of gas and dust illuminated by the intense radiation from hot young suns. These stellar nurseries span light years across, their colors revealing the energies at play: red from hydrogen emissions, blue from reflected starlight, green from glowing oxygen atoms. The energy from young, massive stars ionizes the surrounding gas, stripping electrons from atoms and causing them to glow like cosmic neon signs. Within these beautiful clouds, gravity slowly pulls matter together, converting gravitational potential energy into heat until new stars burst into fusion, a cycle of star formation that has continued for billions of years, each generation forging heavier elements and releasing energy into space. Quasars are among the most energetically brilliant objects in existence, supermassive black holes surrounded by accretion disks of matter spiraling inward at tremendous speeds. As gas and dust fall toward the black hole, friction heats it to millions of degrees, causing it to radiate more energy than thousands of galaxies combined, despite being no larger than our solar system. These cosmic engines shine across billions of light years, so bright that astronomers first mistook them for nearby stars, not realizing they were seeing the most luminous objects in the universe. The energy output from a single quasar can exceed that of 1 trillion suns, matter's final brilliant performance before crossing the event horizon into darkness. The universe is slowly losing usable energy to entropy over cosmic time, a gradual slide toward a state where no work can be done and no differences exist. This doesn't mean energy is disappearing, the total remains constant, but rather that it's spreading out, becoming more evenly distributed and less available for useful transformations. Hot stars cool, gradients flatten, organized structures slowly dissolve into equilibrium. In the far future, trillions of years from now, the universe may reach maximum entropy, all energy perfectly distributed at a uniform temperature. No more stars, no more life, just an endless cosmic stillness. For now though, differences remain, energy flows, stars shine, and the universe stays far from this final equilibrium, still vibrant with available energy. Earth receives about 173,000 terawatts of solar energy continuously, an amount far exceeding all of humanity's energy consumption by thousands of times. This constant influx of energy drives virtually every process on our planet's surface. It evaporates water for clouds, creates wind, powers photosynthesis, warms the oceans and land. If we could capture just 1 hour of the sunlight falling on Earth, it would provide enough energy to power human civilization for an entire year. Yet we use only a tiny fraction of this generous flow, most of it simply absorbed by land and water, reflected back to space or cycling through natural processes that have operated for billions of years, long before humans arrived to harness any of it. Lightning bolts contain up to 1 billion joules of electrical energy, channels of plasma hotter than the sun's surface that bridge sky and ground in spectacular discharge. When storm clouds build up tremendous charge differences, typically negative at the bottom and positive at the top, the electric potential eventually overcomes air's resistance, and electrons surge downward in a zigzag path toward the ground. The main bolt then flashes back upward along this ionized channel at nearly 1/3 the speed of light, releasing energy as brilliant light, heat, and the shock wave we hear as thunder. This natural electricity happens somewhere on Earth about 100 times every second, the atmosphere constantly balancing charge, releasing energy in bright flashes that have awed humans since our earliest days. The Earth's core maintains temperatures around 5,200 degrees Celsius from residual heat left over from the planet's formation and from radioactive decay of elements like uranium and thorium deep underground. This internal heat, roughly matching the temperature of the Sun's surface, has been radiating outward for over 4 billion years, yet the Earth remains intensely hot inside, heat flowing slowly through rock toward the surface. This geothermal energy drives plate tectonics, causes volcanic eruptions, heats deep ocean vents where strange life thrives in darkness, and keeps the outer core molten, generating Earth's protective magnetic field. The heat beneath your feet stretches back to the violent collisions that formed our planet, ancient energy still flowing, still shaping the world. Volcanic eruptions release enormous amounts of thermal and kinetic energy, sometimes equivalent to multiple nuclear weapons detonating simultaneously. When magma, gas, and rock explode from Earth's crust, they can hurl material miles into the sky, generate pyroclastic flows that race down slopes at hundreds of miles per hour, and release heat that melts rock into glowing rivers. The largest eruptions can affect global climate by injecting ash and gases into the stratosphere, blocking sunlight and cooling the planet for years. This violence is Earth's way of releasing internal heat and pressure, geothermal energy built up over centuries suddenly transforming into spectacular destruction and creation, reshaping landscapes, adding new land to coastlines, reminding us of the tremendous power still churning beneath the seemingly solid ground. Ocean currents transport vast amounts of thermal energy around the planet, moving heat from tropical waters toward the poles and cold water toward the equator in a global conveyor belt. The Gulf Stream alone carries as much thermal energy northward as 1 million nuclear power plants, warming Western Europe and making its climate far milder than it would be otherwise at that latitude. These currents, driven by wind, Earth's rotation, and differences in water temperature and salinity, redistribute solar energy absorbed near the equator, moderating global temperatures and influencing weather patterns across continents. This liquid transport system has operated for millions of years, a thermal circulatory system for the planet, moving energy slowly but persistently through vast volumes of water. Earthquakes release energy that has built up slowly in Earth's crust as tectonic plates grind against each other, storing elastic strain for years or centuries before suddenly slipping. When rock finally fractures or slides along a fault line, the stored energy releases in seconds as seismic waves that radiate outward in all directions, shaking the ground sometimes hundreds of miles away. A large earthquake can release as much energy as thousands of atomic bombs, though spread over minutes rather than microseconds, the ground itself becoming briefly fluid, buildings swaying, the solid earth revealing that it's not as stable as it seems. This energy, accumulated grain by grain through imperceptible tectonic motion, transforms in moments into devastating shaking, then gradually dissipates as waves traveling through rock. The planet's magnetic field is generated by energy from the moving molten iron in Earth's outer core, flowing in complex patterns that create electric currents and, in turn, magnetic fields that extend thousands of miles into space. This geodynamo has operated for billions of years, powered by heat escaping from Earth's interior and by the cooling and crystallization of the inner core, processes that drive convection in the liquid metal surrounding it. The magnetic field acts as an invisible shield, deflecting most of the solar wind's charged particles around Earth, protecting our atmosphere from being stripped away and life from harmful radiation. This protective bubble, generated by flowing metal halfway to the center of the planet, channels energy from Earth's interior into a magnetic embrace that makes the surface habitable. Winds are created by uneven heating of Earth's surface by solar energy, warm air rising in some places while cool air sinks in others, the atmosphere constantly trying to balance temperature differences. The sun heats tropical regions more than polar ones, and land warms faster than water, creating pressure differences that set air in motion, carrying energy from hot to cold, high to low. Earth's rotation twists these flows into curving paths, creating the trade winds, westerlies, and jet streams that encircle the globe. Every breeze you've felt, from the gentlest summer zephyr to the most violent hurricane, originates with solar energy converted to atmospheric motion, the air itself becoming a fluid medium for transporting heat and kinetic energy across the planet's surface. Tides carry energy from the gravitational pull of the moon and sun, raising and lowering ocean levels twice each day as Earth rotates beneath these celestial bodies. The moon's gravity tugs at Earth's oceans, creating bulges of water that follow it around the planet, while friction between moving water and the ocean floor and coastlines slowly dissipates this energy as heat. This tidal energy is actually causing Earth's rotation to slow very gradually. Days were once much shorter, and the moon to drift farther away, both bodies exchanging energy and angular momentum over billions of years. Twice daily, trillions of tons of water rise and fall, energy flowing from orbital mechanics to ocean motion to heat, a cosmic dance that has shaped coastlines and marine life since oceans first formed. Photosynthesis converts about 1% of incoming solar energy into chemical energy stored in plant tissues, a seemingly small efficiency that nonetheless powers most of life on Earth. Plants, algae, and some bacteria capture photons with chlorophyll molecules, using this energy to split water molecules and combine carbon dioxide into sugars, storing solar energy in chemical bonds. Though 99% of sunlight is reflected, transmitted, or converted to heat, that remaining 1% trapped by photosynthesis amounts to roughly 100 terawatts globally, about 6 times more than total human energy consumption. Every plant you see, every forest and field is slowly but steadily capturing and storing solar energy, building living tissue from air and light and water, the foundation of nearly every food chain. Earth's atmosphere absorbs and redistributes solar energy constantly, different gases capturing different wavelengths, water vapor and carbon dioxide trapping infrared heat while ozone blocks harmful ultraviolet rays. The atmosphere acts as both window and blanket, letting visible light through but holding onto thermal energy, creating the greenhouse effect that keeps our planet comfortably warm rather than frozen. Air currents transport this energy from equator to poles, from surface to upper atmosphere and back, creating weather, seasons, and climate zones. Without this gaseous envelope capturing and moving energy, Earth's surface would swing between extreme heat where sunlight strikes and bitter cold in shadow, temperatures fluctuating wildly rather than moderating into the relatively stable conditions that allow life to thrive. Geothermal energy from Earth's interior has been flowing steadily for billions of years, heat gradually escaping from the planet's core and mantle toward the cooler surface. This ancient warmth, partly left over from Earth's violent formation and partly from ongoing radioactive decay, emerges at the surface in hot springs, geysers, and volcanic regions, but flows everywhere beneath our feet, usually too diffuse to notice. The total geothermal energy flux is enormous, roughly 40 trillion watts flowing constantly from the interior. Though spread across Earth's entire surface, it averages less than 1/10 of a watt per square meter. This patient outward flow will continue for billions of years more, Earth slowly cooling, releasing its primordial heat in an epic process that spans the entire age of the solar system. Tropical storms can release as much energy as multiple nuclear bombs per second through condensation of water vapor, though most of this energy takes the form of gentle heating rather than explosive force. As warm, moist air rises and cools in a hurricane, water vapor condenses into liquid droplets, releasing latent heat that was absorbed when the water originally evaporated from the warm ocean. This heat release drives the storm's circulation, creating winds that spiral inward faster and faster. A single large hurricane might release heat energy equivalent to exploding a 10-megaton nuclear bomb every 20 minutes, sustained for days. Though this energy spreads across hundreds of miles rather than concentrating in one explosive instant, power expressed as wind and rain rather than shockwave and flash. The water cycle moves enormous amounts of energy through evaporation and condensation, acting as a global energy transport system that moderates climate and drives weather. When water evaporates from oceans, lakes, and soil, it absorbs heat from its surroundings, storing this energy as latent heat in the vapor. Later, when this vapor condenses into clouds and falls as rain or snow, it releases the heat back into the atmosphere, often far from where evaporation occurred. This cycle transports about 80 watts of power per square meter of ocean surface, collectively moving hundreds of terawatts around the planet. Water is a remarkably effective energy carrier, absorbing and releasing tremendous heat during its phase changes, linking Earth's energy budget together through this endless cycle of evaporation and precipitation. Forest fires release stored chemical energy that plants accumulated over years or decades through photosynthesis, returning carbon to the atmosphere and energy to the environment as heat and light. A single large wildfire can release as much energy as a moderate-sized nuclear weapon, though over hours or days rather than microseconds, flames converting solid wood into gases and releasing the solar energy plants slowly captured and stored. This combustion is actually part of many ecosystems' natural cycle, some plants even depending on fire to release seeds or clear undergrowth, energy stored in living tissue periodically returning to the environment in dramatic fashion. The warmth you feel from a campfire is sunlight that struck leaves months or years earlier, finally being released through chemical transformation, completing a journey from nuclear fusion to photosynthesis to flame. ATP, adenosine triphosphate, is the energy currency of all living cells, a molecule that stores and releases energy in small, manageable packets, perfect for driving life's chemical reactions. Every cell in your body produces and uses ATP constantly, synthesizing it through cellular respiration and breaking it down to power muscle contractions, nerve signals, protein synthesis, and countless other processes. The average human body recycles its entire weight in ATP every day, breaking and reforming these molecules perhaps thousands of times each one a tiny battery that powers the microscopic machinery of life. This universal energy carrier works the same way in bacteria, plants, and animals, a chemical language of energy older than multicellular life itself, proof that all living things share common ancestry. Mitochondria are cellular powerhouses that produce energy through respiration, converting chemical energy from food into ATP through a complex series of reactions requiring oxygen. These tiny organelles, once free-living bacteria that formed a symbiotic relationship with early cells billions of years ago, contain their own DNA and reproduce independently within cells. Inside each mitochondrion, electrons cascade through protein complexes in the inner membrane, releasing energy gradually rather than explosively, the biological equivalent of a hydroelectric dam where electrons flow like water through turbines. A single cell may contain hundreds of mitochondria, collectively producing trillions of ATP molecules every second, your own cellular fleet generating the power that keeps you alive, keeps you breathing, keeps your heart beating through every moment. The human body at rest generates about 100 watts of heat energy, roughly the same power output as a bright incandescent light bulb, maintaining a constant internal temperature despite external conditions. This warmth comes from cellular metabolism, particularly in organs like your liver, brain, and heart, which work continuously even during sleep. Your body is a biological furnace, burning fuel in controlled ways, converting chemical energy to mechanical work, to electrical signals, and ultimately to heat that radiates away into your surroundings. This constant generation of thermal energy is why a crowded room feels warmer, why sleeping next to someone else makes you warmer. Each human body a steady source of heat, burning calories simply to maintain existence, to keep the intricate machinery of life operating at the precise temperature it requires. Your brain uses approximately 20% of your body's total energy despite being only 2% of body weight, an extraordinarily high energy demand that speaks to the complexity of thought and consciousness. Even at rest, your brain consumes about 20 watts continuously, billions of neurons firing, maintaining ion gradients, synthesizing neurotransmitters, forming and pruning connections. This constant activity continues during sleep, your dreaming mind almost as energetically expensive as your waking one. Every thought, every memory recalled, every sensation processed requires energy. Neurons using ATP to pump ions across membranes, creating the electrical patterns that somehow become experience. Your brain's hunger for energy shaped human evolution, requiring efficient metabolism and calorie-rich diets. The price paid for consciousness, for language, for the ability to ponder your own existence. Cellular respiration converts glucose and oxygen into usable energy through a series of chemical reactions, breaking down food molecules and capturing their energy in ATP. This process happens constantly in your mitochondria, taking sugar from your bloodstream and oxygen from your breath, combining them to extract energy while producing carbon dioxide and water as waste products. The efficiency is remarkable. About 40% of the energy in glucose is captured in ATP, with the rest becoming heat that helps maintain body temperature. This controlled burning is far more efficient than simply setting sugar on fire, which would release all the energy at once as useless heat, life having evolved exquisite molecular machinery to harvest chemical energy gradually, precisely, capturing it in forms that can power specific cellular tasks. Photosynthesis captures light energy and stores it as chemical energy in sugars, using carbon dioxide from air and water from soil to build glucose molecules. This process, occurring in chloroplasts within plant cells, is essentially the reverse of cellular respiration, using solar energy to push electrons uphill, creating high-energy chemical bonds that store captured photons. The oxygen we breathe is a byproduct of this process, released when water molecules are split to provide electrons for sugar synthesis. Photosynthesis is the ultimate source of nearly all energy in the biosphere, the primary way that sunlight enters the food chain, ancient cyanobacteria having invented this process billions of years ago, fundamentally changing Earth's atmosphere and enabling all the complex life that followed, including, eventually, you. Warm-blooded animals use significant energy maintaining constant body temperature, an evolutionary strategy that allows activity regardless of external conditions but requires much more fuel than cold-blooded alternatives. While a lizard might need to eat only once a week, a mammal of similar size might need to eat multiple times daily, burning calories to stay warm when the environment is cool, cooling themselves through evaporation when it's hot. This metabolic consistency enables high-level activity at any time. Mammals can hunt at night or in winter, remain active year-round, but demands abundant food to fuel the furnace that runs continuously. Your own body burns a significant portion of daily calories simply maintaining 37 degrees Celsius, temperature regulation being one of metabolism's largest energy expenses. Hibernating animals can reduce their energy consumption by up to 98%, lowering body temperature, slowing heart rate and breathing to barely perceptible levels, entering a state of suspended animation for months. A hibernating bear's heart rate drops from 40 beats per minute to as few as 8, its metabolism slowing to a fraction of normal levels, surviving on stored fat accumulated during summer and fall. This extraordinary energy conservation allows survival through seasons when food is scarce, the animal essentially shutting down most bodily functions while maintaining just enough activity to stay alive. Body temperature may drop close to ambient levels, the animal cold to the touch, burning only ounces of fat per day rather than pounds, stretching limited reserves across the long winter sleep. Hummingbird hearts beat up to 1,200 times per minute during flight, requiring tremendous energy to fuel wings that beat dozens of times per second, allowing them to hover and even fly backward. These tiny birds have the highest metabolism of any animal relative to their size, consuming up to twice their body weight in nectar each day to power their incredible aerial abilities. Their heart rate at rest drops to around 250 beats per minute, still remarkably fast, and they can enter a torpor state at night where metabolism slows dramatically to conserve energy until morning brings new flowers to feed from. Every movement, every moment of hovering before a bloom, burns through calories at an astonishing rate, these smallest of birds pushing the biological limits of how fast chemical energy can be converted to motion. Blue whales consume millions of calories daily to fuel their massive bodies, the largest animals ever to exist requiring enormous energy inputs to maintain their size and activity. A single blue whale might eat 4 tons of krill per day during feeding season, filtering countless tiny shrimp through baleen plates, converting this abundance of small prey into the energy needed to move a 100-ton body through the ocean. Despite their size, blue whales are remarkably efficient, their streamlined bodies and powerful tail flukes propelling them through water with grace. The energy demands of such scale are immense, yet the ocean's productivity in certain regions can support these giants, at least when human impacts don't interfere, proving that size and efficiency can coexist when energy resources are sufficiently abundant. Bioluminescent organisms convert chemical energy directly into light through reactions that produce virtually no waste heat, achieving efficiencies far better than human-made lighting. Fireflies, deep-sea fish, glowing fungi, and countless marine organisms create light through oxidation reactions catalyzed by enzymes, producing a soft glow that may attract mates, lure prey, or confuse predators. This cold light is nearly 100% efficient, unlike incandescent bulbs that waste most energy as heat, nature having perfected chemiluminescence over millions of years of evolution. The chemistry is elegant. Luciferin molecules oxidize with help from luciferase enzymes, releasing energy as photons of light, primarily in wavelengths we see as blue, green, or yellow, living things painting the darkness with their biochemical fires. Migration requires stored energy reserves that some birds build up for months, doubling their body weight with fat deposits before undertaking journeys spanning thousands of miles. Arctic terns travel from pole to pole annually, experiencing 2 summers each year, burning through stored energy over weeks of near-constant flight. Bar-tailed godwits fly non-stop for over 7 days from Alaska to New Zealand, crossing the Pacific without rest or food, surviving entirely on pre-migration fat stores that constitute up to half their departure weight. These epic journeys represent extraordinary feats of energy management, birds precisely calculating how much fuel they'll need, storing it efficiently, then burning it gradually over days of sustained exertion. Biological fuel tanks optimized through millennia of evolutionary refinement. Metabolic rate determines how quickly an organism converts food into energy, varying enormously across species and correlating roughly with body size and temperature. A shrew's metabolism burns so fast it must eat nearly constantly to avoid starvation, while an elephant can go days between meals despite its size, its slower metabolic rate requiring less energy per unit of body mass. Your own metabolism operates somewhere between these extremes, influenced by age, genetics, activity level, and body composition, the rate at which your cells convert nutrients to ATP determining how much food you need daily. This metabolic speed affects not just energy needs, but lifespan, heart rate, breathing rate, nearly every aspect of physiology, the fundamental tempo at which life proceeds. Muscle contractions convert chemical energy into mechanical movement, ATP molecules splitting to power protein filaments that slide past each other, shortening muscle fibers and generating force. Each contraction requires energy. Whether you're lifting heavy weights or simply maintaining posture, your muscles constantly working against gravity. The efficiency varies. Muscles convert roughly 20 to 25% of chemical energy into useful work, with the remainder becoming heat, which is why exercise warms you. This molecular machinery of actin and myosin filaments powered by ATP enables every movement you make, from heartbeats to steps to the subtle motions of breathing. Your body's ability to act in the physical world depending entirely on this conversion of chemical to mechanical energy. The human body is only about 25% efficient at converting food energy into work, with the remaining 75% becoming heat, though this seeming inefficiency actually helps maintain body temperature. When you eat a meal containing 2,000 calories of chemical energy, your body captures only about 500 calories as useful work in ATP, the rest dissipating as warmth through various metabolic processes. This is actually better efficiency than most engines. A car converts only about 20% of gasoline's energy into motion, and the waste heat isn't truly wasted, keeping you warm, maintaining the precise temperature your enzymes require. Every calorie you burn produces roughly 3 calories of heat, your body operating as both engine and furnace, converting food to action while warming itself in the process. A single gallon of gasoline contains approximately 120 to 130 million joules of chemical energy, enough to power a car for perhaps 20 to 30 miles depending on efficiency and driving conditions. This energy was captured from sunlight by ancient plants that became crude oil over millions of years, concentrated through geological processes, refined into liquid fuel that releases its stored energy rapidly through combustion. When gasoline burns in an engine, chemical bonds break and reform, releasing heat that expands gases that push pistons that turn wheels, a cascade of energy transformations that ultimately propels a vehicle forward. This remarkable energy density, storing tremendous power in small volumes, explains gasoline's dominance as transportation fuel despite its environmental costs, nature having concentrated solar energy over eons into this potent liquid form. Solar panels convert approximately 15 to 22% of sunlight into electrical energy, semiconductors within them absorbing photons and using that energy to move electrons through a circuit. The panels contain layers of silicon doped with different elements, creating an electric field that captures energized electrons before they lose their energy as heat. While this efficiency might seem low, it's actually quite remarkable. Photovoltaics directly convert light to electricity with no moving parts, no combustion, no waste products. Modern panels can generate power for decades with minimal maintenance, silently turning sunlight into usable energy day after day. The technology continues improving, efficiencies rising, costs falling, making solar energy increasingly practical as a way to tap into the constant stream of power arriving from the sun. LED lights are about 90% more energy efficient than traditional incandescent bulbs, producing the same brightness while using a fraction of the power and generating far less waste heat. Incandescent bulbs waste most energy as infrared radiation, getting hot to the touch while producing light almost as an accidental byproduct. LEDs, by contrast, generate light through electroluminescence, electrons combining with holes in semiconductor material and releasing energy as photons. This process is inherently more efficient, converting electrical energy directly to visible light with minimal heat, meaning more of the electricity flowing into the bulb emerges as illumination. A 10-watt LED can produce the same light as a 60-watt incandescent, saving energy and reducing the heat load in buildings, a small efficiency gain that adds up across millions of bulbs worldwide. Wind turbines can convert up to 45% of wind's kinetic energy into electricity, approaching the theoretical maximum of 59% known as the Betz limit, beyond which a turbine would stop the wind entirely and cease extracting energy. These massive structures, some with blades longer than football fields, turn moving air into electrical power through elegant mechanics. Wind spins blades connected to generators that convert rotational energy to electricity. The kinetic energy in wind ultimately comes from solar heating, creating temperature and pressure differences. So wind power is really a form of indirect solar energy. Modern turbines are engineering marvels, optimizing blade shape, angle, and rotational speed to extract maximum energy from the moving air, silently converting what was once considered merely weather into useful power. Batteries store electrical energy as chemical energy for later use, reversible reactions allowing repeated charging and discharging cycles that make portable electronics possible. Inside a battery, chemical reactions at electrodes create electrical potential difference, and when connected to a circuit, this potential drives current through the device. Lithium-ion batteries, now ubiquitous in phones and laptops, store impressive amounts of energy in compact spaces by using lithium's light weight and high electrochemical potential. Each charge cycle gradually degrades the battery's capacity as electrode materials break down, but modern batteries can withstand hundreds or thousands of cycles. These portable energy stores have revolutionized technology, allowing us to carry power with us untethered from outlets, electricity captured and held in chemical form until needed. A smartphone battery contains roughly 20,000 joules of stored energy, enough to power the device for a full day of moderate use, or run a bright LED flashlight for several hours continuously. This energy, stored in lithium-ion chemistry, powers not just the screen and processor but cellular radios, GPS, Wi-Fi, sensors and cameras, all the complex electronics packed into a device small enough to hold in your hand. When you charge your phone, electrical energy flows in, driving chemical reactions that store potential energy in the battery's electrodes. During use, these reactions reverse, releasing electrical current that powers the phone's components, the stored energy gradually depleting until you plug in again, the cycle repeating hundreds of times over the device's lifetime, your phone essentially running on concentrated chemical potential. Nuclear power plants convert less than 1% of nuclear fuel's mass into energy, yet this tiny fraction releases enough power to generate electricity for cities because the energy density of atomic nuclei is so extraordinarily high. When uranium atoms split in controlled fission, the products weigh slightly less than the original atom, and this missing mass becomes energy according to Einstein's equation. Even converting less than 1% of mass yields millions of times more energy than burning coal or oil, a single uranium fuel pellet producing as much electricity as tons of fossil fuel. This incredible efficiency explains nuclear power's appeal despite its challenges, an almost incomprehensibly concentrated energy source, matter's structure temporarily loosened to release a tiny fraction of its rest mass as usable power. The average American home uses about 30 kilowatt-hours of energy per day, roughly equivalent to continuously running 3,100-watt light bulbs for 24 hours, though actual usage varies dramatically by season, climate, and lifestyle. This energy powers lights, appliances, heating and cooling, water heaters, electronics, every aspect of modern comfort and convenience. Refrigerators run constantly. Air conditioners work hardest on summer afternoons. Electric ovens draw tremendous power when heating. Washing machines tumble clothes through cycles. The electrical grid delivers this energy reliably, usually invisibly, electrons flowing through wires bringing power from distant generators to your outlets whenever needed. This daily energy consumption, taken for granted by most, represents a tremendous infrastructure achievement. Energy captured from various sources, transmitted across distances, always available at the flip of a switch. Refrigerators work by moving thermal energy from inside to outside, using electricity to run a compressor that forces refrigerant through a cycle of compression and expansion that transfers heat against its natural gradient. The interior stays cool not because the fridge produces cold is merely the absence of heat, but because heat is actively pumped out, maintaining a temperature difference with the surrounding room. This requires continuous energy input to fight against entropy's natural tendency toward equilibrium. The fridge working constantly to keep your food cold, running a heat pump in reverse, extracting warmth from an already cold space and dumping it into the warmer kitchen. The refrigerator is essentially an entropy fighter, using electrical energy to maintain organization and temperature difference in a universe that prefers uniformity and lukewarm everything. Friction converts kinetic energy into heat in every moving system, wheels rolling along roads, wind sliding over surfaces, even blood flowing through vessels, some of motion's energy inevitably becoming thermal energy. This conversion usually works against us. It makes machines less efficient, causes wear, requires energy expenditure to overcome. Yet friction is also essential for grip, for brakes, for staying put. When you slide your hand across a table, the resistance you feel is friction converting a tiny amount of your hand's kinetic energy into heat warming both surfaces. This process is irreversible. You cannot gather up that dissipated heat and reconvert it to motion, making friction a one-way street from organized motion to random thermal vibration, entropy increasing, usable energy degrading into less useful forms, though the total remains constant. Insulation reduces energy loss by slowing heat transfer, creating barriers of trapped air or other materials with low thermal conductivity that resist the flow of warmth from hot to cold areas. In your home, insulation in walls and attic keeps indoor heat from escaping in winter and outdoor heat from entering in summer, reducing the energy needed for heating and cooling. Materials work as insulators precisely because they impede energy transfer, their structure preventing easy movement of heat through them, maintaining temperature differences that would otherwise rapidly equalize. Good insulation doesn't add energy but rather prevents its loss, making heating and cooling systems work more efficiently, requiring less power to maintain comfort, a passive energy savings that continues day and night without any input beyond its installation. Electric motors are typically 85 to 95% efficient at converting electrical to mechanical energy, far superior to combustion engines and wasting very little energy as heat. Inside an electric motor, magnetic fields created by electrical current interact with permanent magnets or other coils, generating forces that cause rotation with minimal losses. This high efficiency makes electric motors ideal for many applications, from tiny motors in hard drives to massive motors in industrial equipment, electrical energy becoming rotational motion cleanly and effectively. The small amount of energy lost becomes heat in the motor's windings and bearings, but the vast majority converts directly to useful work. This efficiency advantage is one reason electric vehicles are gaining ground. They use energy far more effectively than burning gasoline to push pistons. Combustion engines lose about 70% of fuel energy as waste heat, hot exhaust gases, and radiator cooling carrying away most of the energy that could theoretically do useful work. Only about 30% of gasoline's chemical energy actually propels a vehicle forward, with the rest heating the engine, the oil, the coolant, and the surrounding air. This fundamental inefficiency is partially due to thermodynamics. Heat engines cannot be 100% efficient, but also reflects practical design limitations, energy escaping in exhaust before it can do work, heat radiating from hot metal surfaces, friction in moving parts. This explains why car engines get hot, why they need cooling systems, and why idling burns fuel without accomplishing anything useful. Most of each gallon's energy simply warming the environment rather than moving the vehicle. Capacitors can store and release electrical energy almost instantaneously, unlike batteries which take time to charge and discharge, making capacitors perfect for applications requiring quick bursts of power. A capacitor holds energy in an electric field between two conductive plates, voltage creating potential that can discharge in milliseconds when needed. Camera flashes use capacitors, building up charge slowly, then releasing it suddenly as a bright burst of light. Computer power supplies use them to smooth voltage fluctuations, absorbing and releasing energy rapidly to maintain steady output. The energy storage is temporary. Capacitors leak charge over time, but their speed and cycle life exceed batteries by orders of magnitude, enabling applications where rapid energy transfer matters more than long-term storage. Kinetic energy recovery systems in vehicles capture braking energy that would normally be lost as heat and convert it back into useful power, storing it in batteries or capacitors for later use. In hybrid and electric vehicles, when you brake, the electric motor runs in reverse as a generator, converting the car's kinetic energy into electricity rather than letting brake pads dissipate it as friction heat. This recovered energy can then power acceleration or accessories, improving overall efficiency by recapturing energy that would otherwise be wasted. The same principle works in Formula One race cars and in regenerative braking systems on trains, every deceleration becoming an opportunity to harvest energy. This technology acknowledges that energy changes form but never disappears, finding clever ways to redirect it toward useful purposes rather than simply letting it dissipate. E equals mc squared reveals that mass and energy are equivalent and interchangeable. Einstein's famous equation showing that even tiny amounts of mass contain enormous energy if fully converted. The c in the equation is the speed of light, roughly 300 million meters per second, and it's squared, making even small masses correspond to tremendous energy values. A single kilogram of matter, if completely converted, would release about 90 quadrillion joules, enough energy to power the United States for several days. This equivalence explains nuclear power, particle physics, and why the sun shines. Though in practice complete conversion is impossible, fission and fusion only tap tiny fractions of mass energy, yet even these fragments release more power than any chemical reaction could possibly achieve. Absolute zero, negative 273.15 degrees Celsius, is the theoretical point where all molecular motion ceases, particles reaching minimum possible energy states allowed by quantum mechanics. At this temperature, gases would become solids, atoms would stop vibrating, and thermal energy would approach but never quite reach zero due to quantum effects. No laboratory has achieved true absolute zero, though scientists have cooled materials to within billionths of a degree, creating exotic quantum states where matter behaves strangely. Absolute zero represents more than just cold. It's a fundamental limit, a boundary where classical ideas of temperature break down and quantum phenomena dominate. In a sense, it marks the edge of thermal energy, the point where heat's influence finally releases its grip on matter. Phase changes like melting and boiling require energy without changing temperature, the added heat going into breaking molecular bonds rather than increasing kinetic energy. Ice absorbs tremendous energy while melting, remaining at 0 degrees Celsius until fully liquefied, the energy used to overcome hydrogen bonds holding water molecules in crystalline structure. Similarly, liquid water boils at a constant 100 degrees Celsius, energy going into converting liquid to gas rather than raising temperature further. This latent heat is why steam burns are so severe. The vapor carries not just high temperature but also the energy required to transform from liquid, releasing this stored energy when condensing on skin. Phase changes absorb or release energy while maintaining constant temperature, material structure changing even as molecular motion stays steady. Chemical reactions either release energy as products form, exothermic reactions like combustion that warm their surroundings, or absorb energy from the environment, endothermic reactions like photosynthesis that require energy input. The difference depends on whether product molecules have lower or higher energy than reactants, bonds breaking and forming with net gain or loss. Burning wood is exothermic, releasing stored solar energy as heat and light, while melting ice is endothermic, absorbing heat from surroundings. Your body runs primarily on exothermic reactions, breaking down food molecules and releasing their energy gradually, using it to drive endothermic processes like protein synthesis. Every chemical change involves energy transfer, bonds holding potential that releases or absorbs as molecular arrangements shift, energy flowing through chemical transformations that power both life and technology. Entropy is the measure of unusable energy in a thermodynamic system, disorder gradually increasing, available energy dissipating into forms that cannot easily do work. The second law of thermodynamics states that entropy always increases in closed systems, organized energy inevitably degrading toward randomness. A hot cup of coffee cools to room temperature, its concentrated thermal energy spreading out, becoming less available, more entropic. Living things temporarily decrease their own entropy by consuming energy from outside, food or sunlight, but the process increases overall universal entropy. Ultimately, entropy drives the arrow of time, making certain processes irreversible, ensuring that energy always flows toward greater dispersal, greater uniformity, greater randomness, the universe slowly sliding from order toward equilibrium. Work is done when a force moves an object through a distance, energy transferring from one system to another through mechanical interaction, the fundamental way energy manifests as change in the physical world. Lifting a book requires work, your muscles applying force through distance against gravity, transferring chemical energy from ATP into gravitational potential energy. Pushing a car requires work, force applied across distance accelerating its mass, kinetic energy increasing. Work connects forces to energy changes, the physical embodiment of energy transfer, how energy moves between objects and systems. Without work, energy might exist but accomplish nothing. Work is energy in action, force and motion combined, the mechanism by which potential becomes kinetic, by which stored energy creates change in the world. Power measures how quickly energy is transferred or converted, the rate at which work is done or energy changes form, typically measured in watts, where 1 watt equals 1 joule per second. A 100-watt light bulb converts 100 joules of electrical energy to light and heat every second, while a 1,000-watt microwave transfers 1,000 joules per second into food. Power doesn't describe total energy, but rather how fast energy flows, the difference between a trickle and a flood, both water but at vastly different rates. A battery might store significant energy but deliver it slowly, having high capacity but low power, while a capacitor might store less but discharge nearly instantaneously, high power but low capacity. Understanding power helps us grasp energy's temporal nature, that what matters isn't just how much energy but how quickly it can be used. Resonance occurs when systems naturally amplify energy at specific frequencies, inputs matching the system's natural vibrations, causing energy to build with surprising efficiency. A child on a swing demonstrates resonance. Small pushes at the right frequency gradually build to large oscillations, energy accumulating with each synchronized input. Bridges can collapse if marching soldiers' footsteps resonate with the structure's natural frequency, small regular forces building to destructive amplitudes. Musical instruments use resonance to amplify sound, their shapes designed to reinforce certain frequencies while dampening others. Resonance is how energy can accumulate dramatically from modest inputs, systems storing and magnifying energy when forced at their natural rhythms, periodic inputs adding constructively until oscillations grow surprisingly large. Quantum mechanics reveals energy exists in discrete packets called quanta rather than continuous values, photons carrying specific amounts of electromagnetic energy determined by their frequency. This quantization, so counterintuitive at human scales, governs atomic and subatomic behavior, electrons only occupying specific energy levels, photons only carrying energy in integer multiples of a fundamental value. This discovery revolutionized physics, showing that energy isn't infinitely divisible but rather comes in smallest possible units, quantum steps rather than smooth ramps. At large scales, these steps blend into apparent continuity, but at atomic scales, quantum nature dominates, energy transferred in discrete chunks, light absorbed and emitted in individual photons, a granular reality underlying the smooth energy flows we perceive. Electrons can only occupy specific energy levels around atoms, unable to exist at intermediate energies, jumping between allowed states by absorbing or emitting exact amounts of energy as photons. This Quantization creates atomic spectra, each element's unique fingerprint of lines corresponding to specific energy transitions. When electrons absorb photons of precise energy, they jump to higher levels, then later fall back down, releasing photons of the same energy, creating the emission lines that let us identify elements across vast cosmic distances. This discrete nature of atomic energy levels underlies chemistry, determining how atoms bond, what wavelengths materials absorb, even the colors of compounds. Energy's quantization at atomic scale shapes the material world, though its effects become invisible at larger scales where countless quanta blend smoothly. Photons are massless particles that carry electromagnetic energy, traveling at light speed through vacuum, behaving sometimes as waves and sometimes as particles depending how we observe them. Each photon's energy depends on its frequency. Blue photons carry more energy than red ones, X-rays more than visible light, gamma rays more still. Despite having no mass, photons carry momentum and can push on objects, pressure from sunlight being measurable, solar sails using photon momentum for propulsion. These quantum particles of light were among the first hints of quantum mechanics, their behavior defying classical physics, existing as probability waves that collapse into definite positions only when interacting with matter. Every ray of light is countless photons, quantum messengers carrying energy across space, connecting sun and earth, eye and object in endless energetic conversation. The joule is the standard unit for measuring energy in science, defined as the energy transferred when 1 Newton of force moves an object 1 meter, a practical unit linking energy to mechanical work. 1 joule is quite small, roughly the energy to lift an apple 1 meter, but it scales appropriately, kilowatt-hours converting to millions of joules, food calories to thousands. Named after James Prescott Joule, who demonstrated energy's equivalence across different forms, showing that mechanical work and heat were interchangeable, the unit honors his fundamental contributions to thermodynamics. Whether measuring electricity, heat, kinetic motion, chemical reactions, or nuclear processes, joules provide a universal language for energy, different phenomena made comparable through this common measure, all energy ultimately expressible in these standardized units. Temperature measures the average kinetic energy of particles in a substance. Faster molecular motion corresponding to higher temperature, slower motion to lower, heat being the bulk effect of countless particles' random movements. When you touch something hot, you feel molecules vibrating vigorously, transferring energy through collisions with your skin. A gas at higher temperature has molecules moving faster on average, carrying more kinetic energy, while a cold solid has atoms vibrating minimally around fixed positions. Temperature isn't energy itself, but rather indicates energy density, the average per particle rather than the total. This microscopic interpretation explains why temperature equalizes when objects touch, faster particles transferring energy to slower ones until average speeds match, molecular chaos establishing thermal equilibrium. Conductors allow easy energy transfer while insulators resist it, materials' atomic structure determining how readily they transport heat, electricity, or both. Metals conduct well because electrons move freely through their structure, carrying charge and thermal energy efficiently, while materials like rubber or glass hold electrons tightly, impeding energy flow. This distinction shapes technology. Wires use conductors to carry electricity where wanted. Insulation surrounds them to prevent energy loss where unwanted. Even within materials there are degrees, silver conducting better than copper, better than iron, each material's particular atomic arrangement creating varying resistance to energy flow. Understanding conductivity lets us direct energy precisely, channeling it through preferred paths while blocking it elsewhere, controlling energy's movement through careful material selection. Thermodynamics describes how energy moves and changes in physical systems through a set of fundamental laws that govern every energy transformation in the universe. The first law states energy is conserved, never created or destroyed. The second law says entropy increases, energy dispersing toward disorder. The third law sets absolute zero as unattainable, a perfect ordering impossible to reach. These laws constrain what's possible, explaining why perpetual motion machines cannot work, why heat engines have efficiency limits, why time has a direction. Thermodynamics applies universally, from steam engines to stars, from cells to ecosystems, a framework describing energy's behavior with mathematical precision, the deep rules governing how energy flows, transforms, and ultimately determines what can and cannot happen in our physical universe. A single uranium fuel pellet, roughly the size of your fingertip, contains as much energy as 1 ton of coal, the incredible energy density of nuclear fuel making it far more concentrated than any chemical source. This pellet, if used in a reactor, could generate enough electricity to power an average home for several months, the uranium-235 atoms within it waiting to split and release the binding energy holding their nuclei together. A reactor core might contain tens of thousands of these pellets, collectively producing gigawatts of continuous power from a mass that wouldn't fill a swimming pool. This concentration explains nuclear power's appeal, tremendous output from minimal fuel volume, though it also means the waste, while small in volume, remains intensely radioactive for millennia, energy's concentration creating both opportunity and challenge. Your body at rest produces enough heat in about 3 hours to theoretically boil a gallon of water, though an athlete exercising intensely could do so in 30 minutes. Your metabolism continuously generating thermal energy as a byproduct of staying alive. At rest, you're a 100-watt heater, mostly from organs working constantly, heart pumping, brain thinking, kidneys filtering, liver processing, all cellular activity generating warmth. During intense exercise, this can increase 5-fold or more, muscles burning through ATP rapidly, most energy becoming heat that must be dissipated through sweating. You are, thermodynamically speaking, a warm-blooded furnace, burning fuel continuously, maintaining steady temperature despite external conditions, each calorie consumed ultimately becoming warmth radiating into the environment, your body's inefficiency at capturing energy actually serving the useful purpose of keeping you at precisely 37 degrees. The energy in a thunderstorm equals approximately 10 atomic bombs, though spread across hours and square miles rather than concentrated in explosive instants, nature's power distributed rather than focused. The latent heat released as water vapor condenses into rain, the kinetic energy in swirling winds, the electrical energy in lightning strikes, all combined might total hundreds of terawatt-hours, more than many cities use in months. This energy comes ultimately from the sun, heating surface water, evaporating it, the water vapor rising and storing energy that releases when condensing aloft. A storm is a heat engine, converting temperature differences into motion, into electricity, into the spectacular display of nature's power. The comparison to bombs helps grasp the scale, though the storm's energy flows over time and space, impressive not for destructive concentration but for sheer magnitude distributed across the sky. Sharks can detect electrical energy fields as small as 1/1000th of a volt, using specialized organs called ampullae of Lorenzini that sense the weak electrical signals produced by other animals' muscle contractions and nervous systems. This extraordinary sensitivity allows sharks to locate prey buried in sand or hidden in murky water, detecting the bioelectrical fields all living things produce. Even Earth's magnetic field induces weak electrical currents in moving seawater, which sharks can sense and potentially use for navigation across vast ocean distances. This ability to detect such minute energy signals represents one of nature's most refined sensors, evolution perfecting electrical detection to levels far exceeding human technology, demonstrating that energy comes in all scales, from lightning's billions of volts to the billionths sharks sense in their ocean realm. The International Space Station's solar arrays generate 84 to 120 kilowatts of energy, 8 large panels capturing sunlight and converting it to electricity that powers life support, experiments, communications, and systems that keep astronauts alive in the harsh environment of space. These arrays slowly track the sun as the station orbits Earth every 90 minutes, maximizing energy capture during each daylight period and storing excess in batteries for the 45 minutes of darkness. The panels must work reliably in extreme conditions, cycling between solar radiation and shadow, facing atomic oxygen and micrometeoroids, operating in vacuum, yet continue producing power year after year. This floating laboratory demonstrates solar power's versatility, sunlight converted to electricity supporting human life 250 miles above Earth, energy captured from the same star that powers life on the planet below. A single bolt of lightning contains enough energy to power a 100-watt light bulb for nearly 4 months, though capturing this energy is practically impossible as it discharges in microseconds, the power released in that brief flash exceeding what most power plants generate continuously. Lightning transfers about 1 billion joules, but this energy dissipates immediately as heat, light, and the shock wave we hear as thunder, arriving and departing too quickly to capture in batteries or capacitors with current technology. The challenge isn't the total energy, which while impressive isn't enormous, but the rate of delivery, tremendous power condensed into a fraction of a second, all that energy flowing through a narrow channel in less time than you can blink. Lightning reminds us that energy has 2 dimensions, the total amount and the rate of transfer, both mattering equally. Plants on Earth store more energy from the sun each year than humans use in a decade. The collective photosynthesis of forests, grasslands, crops, and ocean phytoplankton capturing roughly 100 terawatts continuously, building biomass from air and sunlight. This planetary scale process converts about 1% of incoming solar energy into chemical bonds, a seemingly small efficiency that accumulates to staggering totals when summed across billions of acres of photosynthesizing organisms. Most of this captured energy flows through natural food chains, consumed by herbivores, predators, decomposers, cycling through ecosystems. Even so, the small fraction humans harvest as food and fuel represents tremendous power, nature having perfected energy capture over billions of years, quietly storing solar energy in every leaf, every blade of grass, every microscopic algae cell, the green world a vast, distributed solar collector. The Large Hadron Collider accelerates particles to energies never before created on Earth. Protons racing through a 17-mile ring at 99.9999% light speed, each one carrying about as much kinetic energy as a flying mosquito except concentrated in a particle millions of times smaller. When these protons collide, their kinetic energy converts to mass through E equals mc squared, creating exotic particles that existed only in the universe's first moments after the Big Bang. This machine pushes matter to extreme energy states, recreating conditions from cosmic dawn, using tremendous electrical power to give individual particles energies that seem tiny on human scales but represent enormous concentrations at particle scales. The LHC demonstrates energy's convertibility between motion and matter, using one of physics' most fundamental equations to explore nature's deepest laws by achieving energy densities matched only by the early universe itself. Your heart performs enough work over several days to lift your body mass 1 kilometer high, pumping tirelessly with each steady beat, moving blood through tens of thousands of miles of vessels against gravity and friction. Each contraction does a few joules of work, pushing about 70 milliliters of blood at several thousand contractions daily, adding up over time to impressive totals. Your heart is remarkably efficient for a muscle, extracting energy from oxygen and nutrients in blood flowing through coronary arteries, never resting more than a fraction of a second between beats. This persistent work, continuing day and night throughout your entire life, represents one of biology's most impressive endurance feats, a single organ steadily converting chemical energy to mechanical work for decades, pumping blood enough times to fill multiple Olympic swimming pools, lifting it against gravity repeatedly through its endless circulation. Every breath you take requires about half a joule of energy from your muscles, the diaphragm and intercostals contracting to expand your chest cavity, reducing pressure so air flows inward, then relaxing to exhale, a cycle repeated roughly 20,000 times daily. This continuous work, usually unconscious, consumes a small but measurable portion of your metabolic energy, your respiratory muscles converting ATP to mechanical movement that drives gas exchange. During exercise, breathing becomes harder work, muscles contracting more forcefully and rapidly, energy consumption increasing proportionally. Even this basic act of breathing, so automatic you rarely notice it, represents energy transformation. Chemical energy becoming mechanical work, becoming the pressure changes that move air in and out, delivering oxygen and removing carbon dioxide, the energetic foundation of every other process in your body, the first requirement of staying alive. And so the story of energy circles back to where it began, with you breathing softly, your heart beating steadily, your body warm against the sheets, all of it sustained by energy flowing through countless transformations. From the nuclear fires in the sun's core to the gentle chemistry in your cells, Energy moves and changes but never disappears, connecting you to stars and storms, to the ancient past and the distant future. As you drift towards sleep now, know that you are part of this grand flow, energy coursing through you just as it courses through galaxies and atoms, the same fundamental force in different forms. Rest well in this thought, that you belong to the universe not as a separate thing but as a temporary pattern in energy's eternal dance.